Okay, we're ready to start section 5.2 on the definite integral. So this is riffing off of the ideas that we were looking at in the previous section. So just as a reminder, we were looking at how to estimate the area under curves here with rectangles, and we had three basic ways to do it. We could approximate area using right endpoint rectangles. So in this case, we want to chop it up into three subintervals. We draw rectangles with the heights from the right endpoint of each interval. We can do from the left endpoint approximations with left endpoint rectangles, or we could use the midpoint to construct your rectangles. In this case, I've done it for three rectangles in each case. Of course, we could have as many rectangles, as many subintervals as we want. And so, if you recall, we had this theorem that said we have a continuous function, then all three of the approximations here approach the same limit as n goes to infinity. So there is some L such that the limit as n goes to infinity of the r sub n approximation is the limit as n goes to infinity as the L sub n approximation is the limit as n goes to infinity of the m sub n approximation. So so going back to this section, we're going to say here in the near future, L is the definite integral of f over the interval a to b. So so that's going to be coming up in a little bit. Before we get there, I want to talk a little bit about how we're chopping up our intervals. So in the previous section, we were assuming that whenever we chopped up our intervals that we're integrating over, as well, that's a word I'm going to use for the first time, that we're integrating over, where we're finding the area under the curve on that interval, we're always chopping them into equal size intervals. So in this case, here I've chopped it up into 5 intervals, and it's intended that these are going to be all equally spaced apart. So this is x is equal to 1, and this is x is equal to 2, 1.2, 1.4, 1.6, 1.8, and 2. However, we don't necessarily have to have equally spaced intervals. So we could have, if we want to chop into 5 intervals, we could do this choice, this choice, this choice, this choice, and this choice. So we would just say here x0, x1, x2, x3, x4, and x5. And here you can clearly see that I'm not equally spacing them apart. But we can define approximations over these this kind of subpartition here that is just like we did in the previous section. And if we're going to do this, this is going to lead to the notion of what is called a Riemann sum. So what we did in the previous section with the left endpoint and the right endpoint and the midpoint approximations is a special case of something that we're going to call a Riemann sum. Let me draw a picture for you. And I should say that in addition to changing things, changing how we're slicing up, in addition to changing up how we're slicing our interval, we're also going to now allow our function to be both above the x-axis and below the x-axis. So suppose here that this is my function f of x, and here is my interval that I am integrating over. So I'm going to chop it up into some number of subintervals. So there's a chop line, 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 there's a chop line. So x0, x1, x2, x3, x4, x5, x6, and x7. So I chopped it up into 7 different subintervals. So when I construct my my Riemann sum, what I'm going to do is that for each subinterval, I'm going to form a rectangle, and I can actually choose any point inside of here to provide me with my height. So before we were saying, oh, you always have to pick the left endpoint, or oh, you always have to pick the right endpoint, or oh, you have to pick the midpoint. Now I can choose anywhere I want. So let's say I choose that point. That point gives me that height. So there's my first rectangle. Now let's say I actually just pick basically the right endpoint. So there's another rectangle. For this one, let me suppose I pick right there. So there's a rectangle. For this one, suppose I pick right there. So there's a rectangle. Now, okay, let's say I pick that point right there, just kind of squeeze it in there. Now when I form a rectangle, I'm actually going below the axis. So this is our first time I've seen something like that. Suppose I pick that point there. Again, my rectangle is below the axis. And one last rectangle. So this is what I'm shading in here for all of those rectangles. So we have a couple of differences. Number one, not equally spaced intervals. Number two, we aren't always picking the left or the right endpoint. We're picking some point in the middle. And then number three, we have to think about how to deal with what happens our rectangles being below the x-axis. Seems like that we should want to deal with them a little bit differently. And so how we're going to do it is that we're going to introduce the notion of signed area. So when we talk about signed area, what we mean is that any area above the x-axis is going to come with a plus sign, and any area under the x-axis is going to come with a negative sign. So just as a real quick little example here, so suppose that, 1, 2, 3, 4. Suppose that our function, or even our approximation to our function, look like this, and like this, and like this. So the area here would be base times height as 1 times 2 is 2. This area base times height would be 1. This area would be 1. But this area down here comes with a minus sign because it is under the axis. So the overall signed area here would be 2 minus 1 plus 1. So the overall signed area here is 2. One more thing that we're going to have to talk about is when we take a partition. So the partition is the decision of how we're going to chop things up here. We call our partition P. We introduce this concept called the norm of the partition, which is the maximum of the lengths of the subintervals. So in this case, what's our longest subinterval? Is probably this one. So whatever is the distance from here to here, that would be the norm of this partition. So after we've got all of these ideas here, from signed area, from the norm of the partition, we are finally able to say what exactly is a Riemann sum. So a Riemann sum are of f of p and c. So P is our partition, C is their choice of points inside the partition that we're going to be adding things up over. It is the sum from I from 1 to n of f of ci times delta xi. So what is going on here, this delta xi, that's the width of each of the subintervals in our partition. F of ci, that is we plug in a point into our function, and it will provide us with the height of the rectangle. And if f of ci is negative, we're thinking of our height as negative, it's going to contribute a negative sign area to the overall sum here. So this is what our Riemann sum is. This is our definition.